So today let us talk about some example of measurable function, especially Borel measurable function. We'll define Borel measurable function, and then we'll give some important examples which will be used in the further theories. Okay, so first let us define what do you mean by a Borel measurable function. So a Borel measurable function, we said that a function f is Borel measurable. We said that a function f is a Borel measurable function, or just simply Borel function, if for every real number alpha this set is a Borel set, x such that f of x is strictly greater than alpha is a Borel set. What do you mean by Borel set? A Borel set is a member of the sigma algebra generated by intervals, all sort of intervals. Okay, so let me just first just recall it. Interval means interval of this form: a comma b. So where a, b are real number, and here it is closed and here it is open. So you have collection of such intervals. So this collection of interval will generate a sigma algebra. That sigma algebra, member of that sigma algebra is called a Borel set. Okay, member of that sigma algebra is called a Borel set. So the definition is that function is said to be a Borel measurable function, or simply Borel function, if for every real number alpha this set x such that f of x is strictly greater than alpha is a Borel set. Okay, then we said that it is a Borel measurable function. Now let us give some example, one important example which was used earlier, also it will be using later on, also very fundamental one. Every continuous function is a Borel function. So let us show that every continuous function is a Borel function. Okay, so now for a given real number alpha, let us define b alpha like this: b alpha is equal to x such that f of x is strictly greater than alpha. So if we are able to show that this is a Borel set, okay, then it is done. For each alpha, if we are able to show that b alpha is a Borel set, then it is done. So we know that every open set is a Borel set. Okay, so in another word, if we are able to show that b alpha is an open set, then it is equally done. Okay, so let us see b alpha. So if x is a member of b alpha, according to this definition, what f of x is strictly greater than alpha. Okay, if x is a member of b alpha, f of x is strictly greater than b alpha. So this implies that what? This implies that f of x is a member of this interval alpha. This is infinity, this is alpha. Here it is open, here also it is open. Okay, f is still greater than alpha means f of x lies in this interval alpha infinity. Okay, so that means what? That means x is a member of f inverse alpha infinity. From here, x is a member of f inverse alpha infinity. So for every x in b alpha, x is also a member of f inverse alpha infinity. So b alpha is a subset of f inverse alpha infinity. b alpha, it is a subset of f inverse alpha infinity. And next, conversely, let us take one point from f inverse alpha infinity. Let us take one arbitrary point from this set. So what does it say? It says that f of x is a member of alpha infinity. Okay, this belongs to f of x is a member of alpha infinity. So that means what? F of x is strictly greater than alpha. Okay, so f of x is a member of this set means what? F of x is strictly greater than alpha. So whenever f of x is strictly greater than alpha, then x belongs to B alpha. Okay, according to the definition of B alpha, x belongs to B alpha. That means what does it implies? F inverse alpha infinity is a subset of B alpha. Whenever you take one arbitrary point x from this set, that member is also is a member of B alpha. Therefore F inverse alpha infinity is a subset of B alpha. So from 1 and 2 we have the equality. What is the equality? B alpha is exactly equal to x such that f of x is strictly greater than alpha. This is equal to f inverse alpha infinity. So f is continuous and alpha infinity is an often set. So inverse measure of often set is often, okay, under a continuous map. So therefore B alpha is an often set. Okay, since every often set is a Borel set, so the function f is a Borel function or Borel measurable function. Okay, because every often set is a Borel set. So this is a very important example. I think we have used in the earlier example also, and in the coming theory also this will be used. So very important one. Next, another concept let us define. This is also very important one. If a property holds, okay, if a property holds except on a measure set, on a set of measure 0, then we say that it holds almost everywhere. Okay, the property holds almost everywhere, usually abbreviated to AE. Okay, so let us see one example. Let us see one example. Suppose we have two functions, f of x and g of x, f of x and g of x. There are point x. At those point f of x is equal to g of x. Okay, the function f of x is equal to g of x, and then there are point at which the function f of x is not equal to g of x. If the set of point at which these two functions are not equal, okay, you have a set of point at which these two functions are not equal, the measure of that set is equal to 0. Okay, the measure of the set is equal to 0, then we say that f is equal to gx. F of x is equal to g of x, or f is equal to g of x almost everywhere. Okay, almost everywhere. That means the two functions are equal. Where the inequality happens, the measure of that set is equal to 0. Okay, so this is the concept of almost everywhere, the new definition. Okay, so I told you have to read again and again the new definition, and then you just close the note and then write it again and again, so then the concept will be clear. So this is new concept, you have to do that one. So now let us prove a small result. See, let f be a measurable function. Okay, let f be a measurable function. F is a measurable function, and g is another function such that f is equal to g almost everywhere. G is another function such that f is equal to g almost everywhere. That means where the equality fails, the set of the measure of that set is equal to 0. Okay, and then the conclusion of the theorem is that g is also measurable. Okay, if f is equal to g almost everywhere, f is measurable, then g is also measurable. This is also very important one. Let us prove it. For a given real number alpha, number, so I write it, this is number. So for a given real number alpha, let us put f is equal to x such that f of x is strictly greater than alpha. What is capital F? for this real number alpha, x such that f of x is strictly greater than alpha. And then let us put g is equal to, so what is g? G is x such that g of x is strictly greater than alpha, and h is x such that f of x is not equal to g of x. So according to the given condition, f is equal to g almost everywhere, then the measure of this, according to the definition, then the measure of this h is equal to 0. All right, measure of h is equal to 0 because this is the collection of point where the two functions are not equal. Okay, so the measure of that set is equal to 0. So because f is equal to g almost everywhere, the measure of h is equal to 0. So then what is the symmetric difference? So what is the symmetric difference? Okay, f symmetric difference g. Let us see. So f symmetric difference g, f capital F symmetric difference g. This is according to definition equal to f difference g union g difference f. This is the symmetric difference. So from f you take out g, so what is f? F is x such that sorry, just a minute. I have clicked. So what is f? F is x such that f of x is greater than, strictly greater than alpha. This is your capital F. From this set you take out x such that f g of here g of x is greater than alpha. So let us see this set individually. So for the first one says that x says that f of x is strictly greater than alpha. The second one, from this set you take out x such that g of x is strictly greater than alpha. So that means in this set there may be some point where g of x is less than or equal to alpha. So in one way it says that f of x is strictly greater than alpha. So in another way it says that g of x is less than or equal to alpha, then f of x is not equal to g of x. Okay, because f of x is strictly greater than alpha, and then g of x, from this set you have already taken out x such that g of x is strictly greater than alpha. Then there may be some point here such that g of x is strictly g of x is less than or equal to alpha. So in here what happened in this set, x such that f of x will be strictly greater than alpha and g of x may be less than or equal to alpha. All right, g of x is less than or equal to alpha, then f of x cannot be equal to g of x, because f of x is strictly greater than alpha, whereas g of x is less than or equal to alpha. So there is no chance that f of x is equal to g of x. Okay, similarly here also, here what happened, g of x will be strictly greater than alpha, whereas f of x is less than or equal to alpha. So there is no chance such that f of x is exactly equal to g of x. Okay, f of x is exactly equal to g of x. Also for all point in this set, what happened, f of x is not equal to g of x. For all point in this set, f of x is not equal to g of x, because this symmetric difference is equal to f difference g difference f. So what is f? F means x such that f of x is strictly greater than alpha. From this you take out x such that g of x is strictly greater than alpha. So g of x will be less than or equal to alpha. After taking out this portion, here what happened in this totality in this set, what happened, f of x will be strictly greater than alpha and g of x will be less than or equal to alpha. So similar case will be here also. So that means f symmetric difference g is a subset of f symmetric difference g. It will be a subset of, it will be a subset of H, okay, because H is the set of all point where f is not equal to g. So every point here f is not equal to g, so this will be subset of this one. So that was the explanation. F symmetric difference g is equal to x such that x, okay, f of x is still greater than alpha, simultaneously g of x is less than equal to alpha, or g of x is still greater than alpha and f of x is less than or equal to alpha. So there is no chance that f of x is equal to g of x. So therefore for any point here f of x is not equal to gx, therefore this is a subset of H, okay. But what is the measure of H is equal to 0, measure of H is equal to 0, therefore this being subset of H, measure of this set is also equal to 0, measure of this set is also equal to 0. So what does it say then? F symmetric difference G is measurable set, and in this f is measurable. So from that example we did earlier, if F symmetric difference G, if measure of this set is equal to 0, and if one of the set f is measurable, the other set G is also measurable. So f is measurable because what? F is equal to what? F is equal to this one, x such that f of x is greater than alpha. So since small f is measurable function, this capital F is measurable, okay, capital F is measurable. So measure of this symmetric difference is equal to 0, and one set f is measurable, therefore the other set G must be measurable. This we have done it. G means what? X such that g of x is strictly greater than alpha. So this set G is measurable for any real number alpha. For any real number alpha, this set G is measurable. So from the definition, small g function is also measurable, okay. So this completes the proof. What is the theorem? Let us see. If f is measurable and f is equal to g almost everywhere, then g is also measurable, okay, g is also measurable. So another very important example, this is very important, let us see. Let f be a measurable function and be a Borel set, okay. We have defined what is Borel set. So then inverse image of the Borel set is also a measurable set. So this example, inverse image of a Borel set is a measurable set, okay. If the function f is measurable, the inverse image of a Borel set is also a measurable set. So yeah, we know that a Borel set is a member of the sigma algebra generated by the set of the form. I have briefly told you a Borel set is a member of the sigma algebra generated by set of the form. So now, yeah, it is obvious that if x is a member of this one, then this happen. So this statement implies this statement, okay. This statement implies this statement, and this statement implies also this statement. All right. So that means what? F inverse of AB is equal to x such that f of x is greater than or equal to A intersection x such that f of x is strictly less than B. Right. So this equivalence, implies equality of these two sets. F inverse AB is exactly equal to x such that f of x is greater than or equal to A intersection x such that f of x is less than B. Okay, so you can prove yourself by inclusion method. This is straightforward. Then suppose Suppose AI are the interval of this form, and B is the countable union of such interval. Okay, then what happened? From elementary set theory, what happened? F inverse of B is equal to F inverse of union of AI, and this is equal to union of F inverse AI. This equality is there from the elementary set theory. So what happened here? Let us see. This is a Borel set. Its inverse. This is a simple generator. Okay, this is a generator of a Borel set. So this is a Borel set. Its inverse image is what? Its inverse image is equal to, function is measurable. Its inverse image is equal to intersection of two measurable set, this one and this one. So this is measurable because function f is measurable. This is also measurable because function f is measurable. So their intersection is measurable set. That means what? Inverse image of the interval of such type is measurable. Okay, so that means these set are measurable. Inverse image of AI are measurable. So this is a countable union of measurable set. So if B is a typical Borel set, its inverse image is a measurable set because this is equal to this one, and this one F inverse AI is measurable coming from this one, from this one measurable. So countable union of measurable set is measurable. Therefore inverse image of every Borel set is measurable. All right, so how about a complement? Also we know that, from elementary set theory, A complement, inverse image of A complement is equal to inverse image A, then it a complement. So this equality is there. So inverse image of Borel set of such type is measurable. We know a complement of measurable set is measurable. So this set is measurable. That means inverse image of the complement of a Borel set is also measurable. All right, so what does it say? It says that you have a collection of Borel set. Okay, so you have a collection of sets whose inverse images are measurable. Then it forms a sigma algebra. So in that set, Borel set are also there. Okay, so from this what we conclude is inverse image of any Borel set is measurable. Okay, so these two are true not only for Borel set, for every set whose inverse image is measurable. This is true. These two statements are true for every set whose inverse image are measurable. Okay, so from these two what we have is that the collection is a sigma algebra. What collection? The collection of sets whose inverse images are measurable is a sigma algebra. In that sigma algebra, Borel set is also a member, because easily we have seen this one. Borel set is also a member. So briefly here I have written, in general, the class of sets whose inverse images under F are measurable form a sigma algebra. So in that sigma algebra contains intervals. Intervals means intervals like this. Also we have shown earlier also interval, open interval, closed interval, all are included. They are all Borel set. Okay, so from this what we conclude is that inverse image of a Borel set is measurable. Inverse image of a Borel set is measurable. Okay, so this much I want to give today, and the concepts, all the concepts are new to you, so try to assimilate the concept clearly. Okay, read it again and again, watch it again and again. So if you have some confusion or doubts, you can just call me. Okay,